We looked at an example the other day where there are nuisance variables, earthquake and alarm. John and Mary had both called, and we summed out over earthquake and alarm. And we wrote out this into this big mess. This is why I think Bayes nets are a little hard, especially in a time-pressured situation like an exam, where you're like, you might forget one of these and then get the wrong answer, and it's bad. So you write out all this stuff, and then you say, oh, whoa, that doesn't depend on E, and you move it outside, and then you do this computation. And now you have the probability that burglary is true, because here you're assuming that that's true. And then you have to figure out alpha. How do you figure out alpha? Let's do a little example. Let's do another little example. Again, is that okay? Can we go through yet another Bayes net example? People aren't going to find that repetitious. They might find it helpful. All right, what we're going to do is this. So you wake up in the morning, and you've got a headache. H is true. And you're saying to yourself, I got brain cancer. C. And you're stumbling to the bathroom like, brain cancer, where's my cancer medication? And you look in the mirror, and then you realize that your face is bloody and you've got bruises all over. B is true. And you're like, I just got in a fight last night when I was drunk. It's not a big deal. I don't have brain cancer. I just got in a fight. Okay? That's the explanation for the headache. Right? Fighting causes both bruises and headaches, whereas cancer just causes the headaches. Okay? So let's see if we can do this. What are some good conditional probability distributions? I wanted to hear from students to assess these probabilities, because I'm not nearly as well informed. Would you say that the CPT here for headache, we have fight and cancer. If this is true and this is true, then the probability of headache is probably like really super high, right? 0.99. Okay. And if fight was true but cancer is false, probability of headache 0.9. Okay. Now, we were not out fighting last night, but I'm sorry to tell you, the cancer guy's here. So is that like 0.95 maybe?
Don't know.
Brain cancer? Oh, I don't know. What does C stand for? 0.6? No, way higher than that.
I feel like it's lower than 5.
I'm going to put 0.75 just to get us going here.
At any given point, if you have cancer, you are 0.75 likely to have a headache.
Exactly.
So you're going to have a headache 3/4 of the day?
It's no fun.
Yeah.
When you get my age, you start having friends I have a friend who has cancer, and she is not having any fun, I can tell you.
What cancer is this?
It's probably the early kind, because when it's really late, you're under such heavy drugs that you can't feel anything. And you basically don't get out of bed. Yeah. She has this incision that, since they gave her all these drugs to kill her immune system, so she hasn't healed. So she's had this cut for 3 months. It's really gross. So when you haven't been fighting and you don't have cancer, the probability of having a headache, it's like... Dude, you need more sleep. So we're not modeling sleep here, okay? 0.05? 0.1? 0.05. 1 out of 20 days, maybe? Okay. All right, so that's the CPT for H. What's the prior probability of cancer? Pretty low, right? I don't know, 0.05? Dude, we're not modeling that. This is supposed to be a 4-variable question like the kind you might find on some exam that you're about to take. Okay, the prior for this is 0.1. Prior for fighting. Okay, well, this is going to be specific to CS majors, so it's going to be pretty low. 0.99. I don't mean fighting about which is better, Emacs or VI. I mean,
that's one.
I mean the kind of thing that leads to bruising in the morning and a headache. 0.02. Thank you very much, Nathan, for helping us make progress. Okay, so fighting and probability of bruise. So if fight was T, then this is probably pretty high.
You should see the other guy.
What are we talking here? 0.9? 0.9, yeah. Depends. If you're a really good martial arts person, presumably you can fight without actually like.
We're talking about computer science here. I am familiar with the art of the martial.
Okay. Fighting false, probability of bruise, super low.
Super low.
0.01? 0.001. Okay, great. So now we got a Bayes net. This is a Bayes net, everybody. Now let's compute. It's 100 times more likely than what?
1 in 10.
Than bruising? Since, dude, so many people. I dissected a brain once and it had a cancer, but the person probably didn't die of that. Like you have, like that's why there used to be like 5 or 10 years ago there was this big fad in whole body scanning. Because like, whoa, we got these MRI machines. Everyone loves to look at the pictures. Let's charge them $2,000. You get a full body scan. We give you all these pictures. And people were doing this full body scans and they're finding, holy shit, I've got like 5 cancers. I better go have these $1 million treatments. And that's why all the healthcare costs in the U.S. are going sky high. Because people have these things that they're totally not going to die of, but it just kind of freaks them out a little bit.
But this is cancer that causes headaches. Basically, I have.
Okay, so the query. So what we're going to have, we're going to try and figure out what's going on. I'm wondering if I'm going to be good enough to keep that on the screen while we're computing here. I'm getting a headache just from doing this problem. So we're going to try and figure out probability of cancer given that I have a headache. All right? And I made some fancy-ass claim about there's an alpha and what do we sum over the nuisance variables? What does it say on your slides? What am I supposed to do here? Yeah, we sum over the nuisance variables, which are this F and B. Not B?
Because it's not in the blanket.
Yeah, it's not under the covers with us. What? Okay, I'm fine with that. So we have to sum over F. The probability of everything. Probability of C, F, and H. Okay, I think we're on the right track so far. Okay, so now what's this? Well, let's see. I'm going to start using the width here. So F, so we've got alpha times some big sum. And right now we're going to do the F equals true case. So it's the probability that, and we're going to do the true case as well. We're going to do the true for this. Oh, and headache was true. And now we're going to do F is true. So we've got C is true, F is true, H is true, plus, right, because we're summing over F, so it's the probability that C equals true, F equals false, H equals true. Okay, everybody, we're all on board here? Okay, so this is going to be alpha times, now what's this joint here? Who gets to go first? How about Adam? Adam, tell me how to compute this joint right here.
All right, so we're going to go to the table. Probability that C is true.
F is true and H is true.
Right, so C is 0.1.
So exactly, so it's 0.1
And the probability
times,
that F is true is going to be, cut it off a little bit, 0.2.
whoops, sorry, 0.02, yeah. Matt, we're going to need a calculator here.
And the probability that H is true, given that C is true and F is true, is 0.99.
Awesome. Anybody know what, Matt, what is this? Matt's our calculator. Matt's our computer. Matt is a computer. All right, who's doing the second joint? Anybody want to volunteer before I pick Nathan? Dan, go and...
C is true is going to be the same. It's going to be 0.1.
You got it. Now F is false.
F is false is going to be 0.98.
Yes, sir.
And then you go to the table for the next one, and it's F is false, C is true, so it's 0.75.
Okay. Do we have any numbers for these, Matt?
Yeah, the first one is 0.00198.
Okay.
Second one is 0.0735.
And what happens if I try to take their sum? Yeah. I'm sorry. If I were smart, I would know how to add two numbers. I guess the last one is going to be a 3. 0.07548. 548. You are allowed to bring a calculator to the exam. Okay, cool. So that's the positive case. So let's do the negative case. And then we know they're supposed to sum to 1. So now we're going to compute the probability that C is false, that we don't have cancer, given that headache is true. All right, and it's going to be alpha times, we have to sum out over F, the probability that C is false, F is whatever it is there, and H equals true. I'm going to just see if this works. This is called scrolling. There, split window technique. All right. So, now let's do the F equals true case. So this is the probability that C is false, F is true, H is true, plus the, let me do it over here, plus the probability that C is false when F is false. And headache is true. That is for sure. Okay. Who would like to go next? Dylan.
C is false is 0.9.
Mm-hmm.
F is true is 0.02.
Mm-hmm.
And H being true, given that F is true, and yeah, so that's what's over under.
Okay. This other case. Joe, bring it home.
C is false is 0.9. Probability that F is false is 0.9.
Whoa, 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 whoa.
0.98.
Yes.
And then probability that H is true given that C is false and F is false is 0.05.
Yes, sir. Matt, can you come to our rescue here? This is going to be like a 36. No, it's not. It's
The first one was, the sum, you just want the sum of them?
well, what's this if you multiply these three numbers together?
0.0169.
0.169, and this other one was
0.0441.
0.441. We add these up. 0.061. Okay. All right. Now, we know that the probability of C being true when H is true and the probability of C being false when H is true have to add up to 1, right? Because that exhausts the the situation, all possibilities for C, true and false. It's just a binary variable. So we know that alpha 0.07548 plus alpha 0.061 equals 1. So this is just alpha. Matt, could I ask you to do a division for me? Could you divide 1 by 0.07548 plus 0.061? I guess you should probably do an addition first before you do the division. Yeah. Can you add these two numbers? They're 0.0 something, so this is going to be like, I'm guessing about 0.14 or 0.139 or something. 3648. Okay. Could you divide 1 by that, please? Dan is racing you. 7.32. Okay. Great. So if we go up here, can you multiply this thing by 7.32? It's good. Does everyone see how this works? This looks like it's going to be 7 times 7 is like 49-ish. 0.55. Oh my gosh, that's sad. Okay, keep going. This one times 7?
I feel like we just made the base net for WebMD.
We just made what?
I feel like we just made the base net for WebMD. What was this?
Oh yeah, this is way better though, because this one is crowdsourced. Can you multiply 7.32? 0.4475. Okay, so the probability, so you wake up with a headache, the probability that you have brain cancer, 0.55. Not good. Not good. I'm not saying our model isn't good, although some may have issues with it, but I'm just saying you wake up in the morning, it's not looking too good with the headache. Now, after you've looked in the mirror, do you guys want to do this yourselves as like an exam, like test kind of situation? Or should we do it interactively in class? No. Let's live it. Let's live the example.
I will match you in fisticuffs.
No. Okay, so now you look in the mirror and you realize, man, I'm all bruised and bloody. Bruised and bloody. That's what the B stands for. Okay, so what's the probability that cancer is true given that H is true and B is true? Okay, it's a different problem. All right. Let's see if we can do this. We're going to have to sum out over F the probability of F equals whatever it is in the sum, and C equals true, and B equals true, and H equals true. This is alpha times some big huge mess. Let's do the true case first. Who hasn't gone? Go. So this is just the problem of F equals true, C equals true, B equals true, H equals true.
Well, F is just
0.02
times 0.1
Mm-hmm.
C times 0.9 for B
Mm-hmm.
and 0.99 for H.
Okay, and now let's do the false case. Who's going to do the false case? Evan. So this is the probability that f equals false while c equals true, b equals true, and h equals true.
0.98.
Yes.
Times 0.1
Yes.
times 0.001 times 0.75.
Excellent. Now, let us call upon our computer. Matt, what do we have here? 0.02 times 0.1 times 0.9 times 0.99. 00172. And what is 0.982? Okay.
Sorry.
What did you get, Matt, for the first one?
0.001782.
Oh, okay, great. I'm glad we're not in an exam situation. What's the next one?
0.0000735.
Okay, what happens when we add these puppies together?
That sums to 0.00185.
Okay, great. All right, we're making progress here. So now we're going to do the the negative case. What's the probability, because we have this annoying alpha. If we didn't have this alpha, then we'd be done, but we have the alpha, so we have to compute the corresponding probability that actually we don't have cancer, even though we woke up with a headache and we're bruised and bloody. So we still have to sum out over f. Probability of f is whatever it is, and c equals false, and b equals true, and h equals true. And this equals alpha times, scroll my window here. Okay. Who hasn't gone yet? Frank! Let's do the true case for f.
Okay, so we start with 0.02, and the cancer is false, that's 0.01, that's 0.1.
Just keep spitting out numbers, and eventually one of them will be correct.
And B given that is true is 0.9, and given
F is true, and C is false.
that's also 0.9.
Okay. And let's see. Kendall, do you want to do the false case here? F equals false.
0.98, that's 0.9, that is also 0.001, and false, that's 0.05.
Now, what do our computers have to say about these?
Okay, so for the true case, it's 0.01458. For the false case, it's 0.0000441.
Did I get the right number of zeros in the beginning here? Or is there supposed to be 2 zeros?
No, that's right.
Okay. And what happens if we add those guys together?
0.0146.
0.0146. Okay, great. Where are we off here?
And really, really small numbers.
Okay, I only care about 3. If you get 3 or 4 digits, I'm going to be happy. And I mean significant digits. After all the zeros. Then I'm going to be perfectly happy. Okay, so now we know. We look at both cases and we say, aha, alpha times 0.00185 plus alpha times 0.0146 is supposed to equal 1. So can somebody please help me figure out what we should divide 1 by? 0.01465. What? Yes.
I heard 645.
Oh, okay, great. So I'm sorry, 0.0. What?
You're up the wrong. You need to scroll.
Oh. Anyway, where are we here? Alpha equals 60.79. Okay, so what does that bring us to here? Why am I listening to you? You gave me a wrong answer before.
That's true.
Give me a probability. 60.79 times 0.00185. 11.112. Okay, and what do we get down here? 88 what? 888. Yeah, great. Those add up to 1. Fantastic. So, wow, did you see what happened? Did you just see what happened? That was total magic. Where's the Bayes net? There's the Bayes net. So, at first, we had the probability that you had cancer of being 55% when you woke up with the headache. But once you looked in the mirror and saw that your face was bruised and bloody, the chance that you were suffering from cancer went down to 11% because there was an alternative explanation for the headache. That phenomenon is called explaining away. And it's very intuitive. Like, I presume if you were in this situation and you discovered the additional facts about the state of the world, your belief in cancer would also drop because the prior is pretty low, right? So that's a really cool thing about Bayes nets, that they give you this explaining away phenomenon. Plus, we got to do all that multiplication.